Okay, topic 5.5 and 5.7. 3D equation of equilibrium. This is what we will discuss in this video. So in the previous video, we talked about equilibrium of a rigid body in 2 dimension. Now we will talk about 3D free body diagram and equations of equilibrium, constraints and statistical determinacy. Objectives are identify support reactions in 3 dimension and draw a 3D free body diagram and apply the equations of equilibrium in 3 dimension. If a support prevents rotation of a body about an axis, then the support exerts couple moment on the body about that axis. Remember, when support prevents translation, it exerts force, but when support prevents rotation, it exerts couple moment. When doing a 3 dimension problem analysis, you have blank number of scalar equations of equilibrium, and the correct answer is 6. So this is an application of 3 dimension object. On the left side, we have a spherical joint. On the right side, we have 2 bearings, and those are being supported. Those are being used to support the other objects, such as the shaft. Then how can we determine the forces applied by the supports at these joints? So ball and socket joint and journal bearings are used in mechanical systems. To design the joints or bearings, the support reactions at these joints and the loads must be determined. The tie rod from point A is used to support the overhang at the entrance of a building. It is pin connected to the wall at A and to the center of overhang at B. So it's talking about this tie rod. So it's connected here and here. If A is moved to a lower position D, will the force in the tie rod change or remain the same? And the answer is it will change. So by making such a change without understanding if there is a change in force, failure might occur. So we should not try to just move this from A to D because it looks good without even in any engineering analysis or calculations, because then the amount of force in the rod will be much larger if we move from A to D, and it may or may not be able to handle the weight of the overhang, and that will lead to failure. So the floor crane, which weighs 350 pounds, is supporting oil drum. That's here. How do you determine the largest oil drum weight that the crane can support without overturning? So if we keep on increasing the weight of the oil drum, at some point the crane is not strong enough to support the oil drum, and it may actually overturn. So what is the largest weight that we can add here, and the crane will not overturn because of that? So these are the example of some types of supports in 3 dimension, such as a smooth support. So when it's a smooth, when we use word smooth, that means we neglect the friction for that matter. So no friction when it is smooth. So if smooth pin, then there is only one support reactions. If it is ball and socket joint, then there are 3 support reactions. Some of the force, like force in X, Y, and Z. When it's a single journal bearing, there are 4 support reactions: horizontal, vertical forces, and 2 couple moments, because this bearing will not allow the shaft to rotate about in this direction, as well as it will not allow the shaft to rotate about this vertical axis. So there are 2 support couple moments that it's applying. Single hinge permits only 1 degree of freedom, that is rotation about this center of axis. Everything else is being restricted here. So for each restriction, there is 1 support reaction. So 3 linear support reaction forces and 2 couple moments. As a general rule, if support prevents translation of a body in a given direction, then a reaction force acting in the opposite direction is developed on the body. Similarly, if the rotation is prevented, a couple moment is exerted on the body by the support. These are a few more examples of support reactions, where you can see how different, like these types of support, they prevent certain reactions and how are they being identified in the diagram. So support reactions are, sorry, the equations of equilibrium are only two, like sum of the forces in x equal to 0, sum of the moments about any point equal to 0. If we expand this vector equations into scalar equation, then we get 6 equations. From one vector sum of the forces, we can get 3 scalar equations. Sum of the forces about x, y, z, and same goes for the moments, sum of the moments about x, y, z, and they all are 0 if the rigid body is in equilibrium. So we have 6 equations of equilibrium for 3-dimension system. That means we can solve up to 3 unknowns. If we have 6 unknowns, if we have more than 6 unknowns, we cannot solve that. It's called statistical undeterminate situation. However, sometimes there are redundant constraints. Redundant means when a body has more supports than necessary to hold it in equilibrium. It's called statistically indeterminate situation because there are more number of unknowns than number of equations. Are statistically indeterminate structures used in practice? Yes, it is possible. Just for the extra safety, we may add additional like redundant constraints, which make the problem statistical indeterminate, but it's good for the safety. Improper constraint. For example, if this bracket is being supported only A and B using this ball and socket joint, then this body is not in equilibrium. Means it's not stable because when the force is applied in vertical direction, it will have tendency to rotate in this plane about this line, and that's called improper constraint. Similar to that, another example, we have pin here and we have roller here. That does not make this beam fully constrained because when the force is applied at an angle, it may result in rotation about A because A is pin and B is roller. So this is also called improper constraint. So in the next video, we will look at in-class exercise 2 problems, and we apply this 3D equations of equilibrium for problem solving. Thank you.